once one of them can't get any more scheduling slots, they hand over to the other cell. So which means that so they attack, and once they can't get any more slots, each of them switches to the other cell, and then they repeat this attack once again, and then until each one of them can't get any more slots, and they stop, and they switch again. Okay, so they can continue this forever. Then we measured the effectiveness of this attack. So we ran a simulation for about 30 seconds to see, of the 30 seconds, what's the percentage of scheduling slots that the two cell phones can get. Remember, there are at least one cell phone per cell. So we looked at how many total slots that the attackers can get based on the number of attackers per cell. Remember, each cell has 50 users. So we learned that if there's only one cell phone per cell, the cell phone can get about 80% of all the slots in that cell. Okay, so just one cell phone, one malicious cell phone out of 50 cell phones in a cell can get about 80% of all the scheduling slots. And if you increase the number of malicious cell phones in a cell to 5, in total they can get about 90%, more than 90% of all the scheduling slots in that cell. Remember, I mentioned earlier that we made this simplistic assumption that the attackers knew the precise channel condition indicator of all the other cell phones. But this is not realistic. Most likely, the attackers do not know the channel condition indicators of other cell phones. So in this case, how can the attackers decide what channel condition quality to report? Well, remember that the attacker only needs to calculate the maximum ratio. Okay? They don't really care about the precise the precise CQI. They only care about the maximum ratio. But the attacker does not know everyone else's ratio. Well, our solution is that we let the attackers estimate the maximum ratio of all the other cell phones. And here's how we estimate it. Suppose at a time slot, the maximum ratio among all the other cell phones is C of t. Now, from that point on, the the attacker can estimate future maximum ratios based on this formula. This is very similar to the sliding window that you saw earlier. So if the attacker is scheduled, then we increase the estimated maximum by a rate of 1 over 1 minus epsilon. So this is based on the intuition that if the attacker is scheduled, then all the other cell phones are not scheduled. So which means that the throughput of all the other cell phones will decrease because they're not scheduled. So therefore, that ratio will increase by a constant factor. Okay, so that's the intuition behind this. However, if the cell phone is not scheduled, then we modify the maximum ratio by this. I won't go into detail of how we arrived at this. Then we ran the simulation again for 30 seconds to see how effective this attack remains if the attackers do not know the precise channel condition of all the other cell phones. Well, we learned that in this more realistic condition, the attack is not as effective as in the ideal condition, but it's still pretty good effective. If there's only one attacker in every cell of 50 users, then this one attacker can get about 75 of all the scheduling slots. Whereas if there are 5 attackers in a cell, then the attackers can, in total, can get about 80% of all the slots in the cell. I mentioned that we used we used a formula to estimate the maximum ratio among all the other cell phones. How good is our prediction? Well, so this graph shows you how good our prediction is. So the y-axis shows our prediction accuracy, which means that among all the predicted values, which of them are the correct values. So we show that it doesn't matter how many attackers there are in the cell, our prediction accuracy consistently remains above 90%. You have to look at the effect of the impact of the attack in terms of how many scheduling slots that the attackers can get. But how does that translate to something that ordinary people can understand? In other words, how does that affect real applications? Well, so first we looked at the throughput. Before the attack, every cell phone in the cell gets about between 40 to 50 kilobit per second throughput. Okay, assuming that every cell phone has similar channel condition. However, after the attack, if there's only one attacker in a cell of 50 users, then that one attacker can get 1.5 megabit per second throughput, whereas all the other victim users get about 10 to 15 kilobit per second throughput each. So that's about 3 times the drop. Yes.
Do you get more bandwidth as there's more people, or is there less for you to steer?
There's a fixed amount of total bandwidth. Okay. So each cell has a fixed total amount of bandwidth determined by what frequency they're using.
But I mean, like, the more users you have on the network, does that mean like the more you can, like, it's harder to steal all the? Do the percentages go down as you increase the users?
Percentage of what?
Of the bandwidth.
Stolen by.
That you can steal. Does it go down as you have more users added to the network?
I see. So are you saying that if I have 100 users in the network, will it be harder for the attacker to get
1.5 megabits?
Yes, that's true. That's definitely true. However, on the other side, the more users there are in a cell, the less bandwidth that the user gets to start with. So once the attack happens, each victim user will get even less bandwidth. Right. So if your application depends on the availability of bandwidth and the amount of delay, then this attack would affect the victim users even more. It depends on the goal of the attacker. If the goal of the attacker is just being selfish, then of course the attacker wants to get as much bandwidth as possible. So in this case, you wish that there are fewer users in the cell. Right? So the fewer users there are in the cell, the more bandwidth the attacker can get. However, if the goal of the attacker is to wreak havoc in the network, then you wish that there are as many users in the cell as possible, because that way you can adversely impact the victim users even more. Okay, so we have looked at the impact of the attack on the bandwidth, but certain applications are delay sensitive. Okay, so what's the impact of the delay of the attack? So before the attack, again assuming similar channel conditions of all mobile users. Before the attack, there are about 10 millisecond average delay between 2 consecutive transmissions, okay, on every user. After the attack, where there's one attacker in a cell of 50 users, after the attack in a cell of 50 users, one attacker can cause